Taipei 101 is one of the world's tallest skyscrapers of 508 meters height, with the most high-tech engineering and construction on the planet, mixing ancient values with cutting-edge technology. Designing and building a skyscraper is not an easy task. But here, especially in Taipei, three factors of nature were combined to make this project not only the tallest and most visible in the world, but also one of the most difficult to build. Taipei City is an inhospitable place to build a skyscraper. Beneath the earth, a thick layer of soft clay demands uniquely designed foundation, while above ground, the threat of two most powerful forces of nature, earthquakes and typhoons, require a level of engineering and construction never achieved before. Taipei 101 was the only super tall building in the world that was designed in a seismically active zone. Our team has been studying about this another level of engineering and construction technology over a semester, about how engineers confronted the power of the nature. Today, we are going to go through the design issues one by one, from design to the completion of the building. Let's start with the seismic design. Keeping the location of Taipei 101 in mind, it is easy to know that earthquake was a worry when designing Taipei 101. To overcome this, Taipei 101 ended up having special structural members compared to the ordinary buildings around us. Core bracing, outriggers, super columns, and perimeter moment frames with reduced beam sections. Bringing such a tall building into reality was a challenge at that time, and the engineers had to figure out some new ways and had to combine some methods to successfully build Taipei 101. The first structure they thought of was tube structures, which were highly reputed in resisting lateral loads in skyscrapers. There are mainly three types, as you can see here, and the first two were eliminated since they took up too much space inside. So the one that was left was framed tube system, and it was nearly considered the best only if the three major drawbacks when applying this to Taipei 101 were solved. Blocking the wide glass expanses desired by the owners, requiring indirect load transfers at the setback atop of each module, and involving intrusive internal beams to connect building faces across the sawtooth corners, which will be explained later. To overcome these, engineers came up with a system including outriggers. Generally, when a building is exposed to lateral forces, it bends in the direction of the force. However, if an outrigger is installed, it resists rotation of the core by improving stiffness and reducing overturning effect, which reduces lateral deflection of core. This outrigger system solved not only the problems that framed tubes had, but also made it possible for the change of the shape, inclination of the exterior skin. Two more structures were used to bring this to reality: core and columns. In the case of Taipei 101, core exists in a special concentric brace frame. It is the kind that focuses more on the ductile behavior and inelastic deformation, which is the key of preventing the collapse of the building against earthquake. Super columns takes place along the perimeter, which are connected to the core and directly to outriggers. More to this, an ordinary-looking moment frame is used. A strong earthquake causes plastic hinges at the end of the beam, in a fully restrained moment frame. So, usually, to counteract these plastic hinges, the strength between beam and column connection is enlarged. But since this method costs too much, Taipei 101 applied a dog-bond beam, reducing the beam section. It might seem counterintuitive that removing a portion of structure improves the performance. But the dog bond results in only a small reduction in lateral strength and stiffness of a frame and provides a large increase in ductility, the key to surviving strong earthquakes. One big structure consisted of brace core, outriggers, and super column is grouped as megaframe, the one that I mentioned earlier. Brace core and perimeter moment frame is called special moment resisting frame. Building the height of Taipei 101 requires not only one, but both of them as a dual system. In Taipei, the environment that needed to be handled was not only seismic problems, but also the wind.
When you put a tall building on an old secondary earthquake fault line, which runs nearby here, and in a place where you get significant typhoons, that just has major challenges.
Taipei 101 is influenced by aggressive typhoons generated on the equator every year. Typhoons accompany strong winds up to 200 kilometers per hour. Not considering it carefully, the building might be in danger under the threat of wind. When a thin, long building like Taipei 101 comes across wind, spiral-shaped airflow, which is called vortex shedding, causes a building to sway in a perpendicular direction of it. When the frequency caused by the vortex shedding becomes equal with the natural frequency of the building, the magnitude of the sway increases amazingly. In general, we make the structure very stiff against wind. But in the case of Taipei 101, it also must be flexible enough because of the earthquake. The engineers came up with an idea of redesigning the exterior of the building. Designing the facade aerodynamically, they could restrain the influence of the winds to tower, including vortex shedding. The softening corner method was applied between the aerodynamical designs, sawtooth, and a double notch. It reduced crosswind response effectively. It showed 40% reduction in wind force. Although the influence of the wind reduced, the energy grows while the sway builds up. To prevent the energy building up, tuned mass damper, TMD in short, is used in Taipei 101. It is extremely heavy, weighing 660 tons. This massive damper acts exactly during the same period and exactly in the opposite direction. The reversed movement of the tower and the TMD cancels each other. And under the mass block, the active viscous dampers transfer the kinetic energy to thermal energy. By even controlling small vibrations caused by the wind, it presents comfort to users inside. Additionally, two small versions of this tuned mass damper, which follow the same principle, is located near the pinnacle, preventing wind fatigue on the steel frame. Taipei 101's unique megastructure and damper resist earthquake and wind shakes. But all of this is meaningless unless a huge building has a solid foundation that exists on solid ground. Due to the change of the sea level over hundreds and thousands of years, Taipei Basin was filled with soft soil and clay. In order for one of the tallest buildings in the world to stand, it had to break through an 80-meter thick layer of soil and find a solid rock beneath it. As a result, it took 15 months to prepare the foundation alone, and about 700,000 tons of soil were removed from the site. It was designed to be held underground bedrocks due to an unstable ground, and it secured under 23,000 square meters of concrete slab through 382 reinforced concrete piles. For Taipei 101, 3 types of foundation were considered: caisson, barrette, and large diameter board piles. They all show high resistance to large lateral loads. However, among these, board pile was chosen to transfer the loads downward in Taipei 101. Based on full local experience, deep excavation was easily achieved. These characteristics made the foundation much stronger. And then, as a solution of the soft foundation below, slurry wall is used. Slurry wall was an on-site laying pile construction that uses a stabilizing solution to excavate the ground and form a continuous reinforced concrete wall inside the ground. It prevents not only water, but also the collapse of soil during construction. So far, we have identified issues in the design of Taipei 101, and now we will deal with the construction process and related issues. The construction of the main megastructure of Taipei 101 began in September 1999 after the foundation was firmly established with slurry walls and board piles. The main megastructure was designed with a concrete-filled steel tube, which had to be weldable, rigid enough to withstand the massive volume of the building, and flexible enough to not fail when shook by earthquake. Because each of these factors require different types of steel, Taipei 101 used 5 kinds with specific flexibility and strength ratios, which were designed for the purpose and location of the building. Each super column box section took 4 months to make, and each one of them had a total of more than 400 joints, 50 of which required enormous work to combine into one seamless unit. It took at least 14 hours to join each joint and worked for almost 2 years. These long hours of effort led us to a robust and flexible super column that can withstand earthquake waves. However, the super steel column was not enough to withstand the building's immense weight. To prevent this huge compressive load from making the steel structure to sink, the middle part of the steel column was filled with concrete. As a result, the tensile strength of steel and the compressive strength of concrete were combined to complement each other, completing a more stable structure. In addition, technicians of Taipei 101 developed a concrete mixture that was about 60% more powerful than the conventional one, and it was used to complete the backbone of the lightest and most flexible building on Earth. At 8 to 3 local time on 31st March 2002, an earthquake of 7.1 on the moment magnitude scale struck Taiwan. The epicenter was offshore from Hualien, located 135 kilometers away from Taipei. It wreaked havoc on the construction site of Taipei 101, and construction cranes toppled 240 meters to the ground, resulting miserable death of 5 workers and injuring dozens more. Immediately, all the works were pulled to a stop, and engineers and surveyors began to look for any structural damage on the building. The survey, which was expected to last 4 weeks, was conducted for 3 months due to the continuing aftershocks. Finally, in July 2002, engineers and surveyors diagnosed that Taipei 101 was intact in its internal structure and could resume the work once again. Although permission to restart the construction was acquired, Taipei 101 still had one problem to solve: the cranes. Since 2 cranes fell on the ground during the earthquake, new ones were needed, and reinforced structures had to withstand the threat of the earthquake. Therefore, work was carried out until September to install the cranes and to reinforce the existing cranes to have capability against earthquake. After that, the erection resumed. In July 2003, construction was carried out to the 92nd floor. It was almost completed, but Taipei 101's mascot, tuned mass damper, was yet in place. The tuned mass damper, as mentioned earlier, is the building's most important windproof structure, designed to counteract the horizontal sway of a huge building. Mass damper has been used in high-rise buildings before, but this was the very first time in its shape, size, and height. In order for the damper to perform a proper function, it must be 1/10 of the total mass of Taipei 101 building, which was a massive weight, nearly 660 tons. Even a crane built for Taipei 101 could not lift such a heavy thing at once. Thus, the TMD was broken into several pieces, lifted to the 92nd floor, and welded in the field to form a complete bowl. A viscous damper was then connected to a 16 meters thick cable, completing the building's most important shield. Most of the buildings were completed in December 2004. The buildings that had been built so far were great, but they were 4 meters short to set a record. Successfully raising the pinnacle would give it the title of the tallest building in the world, but the weight of the pinnacle was by no means light. Like TMD, lifting pinnacle of this size and height was an unprecedented, dangerous, and difficult task. A system of hydraulic jacks and geared cables lifted the massive structure from its base. 14 days since the work started, the pinnacle was perfectly fixed at the top of the building, finally ending 5 years of a long journey. We are now finished on looking through the building from design to completion. The Earth was the biggest overwhelming enemy for Taipei 101, but the engineers took over and succeeded on making the super tall skyscraper. Inside and out, Taipei 101 pushes the boundaries. A unique-looking building changed the face of construction design and engineering for good. It has become a symbol for the future that took on nature and won. Thank you all for being with us through this semester.